All right. Yes. So as we were saying, the maximum load is 130 kilonewton. The maximum load, the maximum load is 130 kilonewton. So let's quickly pull that down as nicely as we have done. And that is what we have done over here. 130 kilonewton. We said that the kilo is already at the top, so there will be no need to write it again. There will be no need to write it again because the kilo is already at the top. From here, what are we supposed to do next? Let's go back to read the question. You see the question there, you always have to be visiting the question, okay, to be sure of what you are doing. The maximum load is 130 kilonewton. The total extension at fracture is 56 millimeters. So let's go and even write it before we. So the total extension at fracture, it means that some breakage went on somewhere. So the total extension at fracture, and the total extension at fracture was 56 millimeters. So let's put that down. This is 56 millimeters. 56, 56 millimeters. 56 millimeters. 56 millimeters. That is 56 millimeters. So from there, what are we supposed to know next? And the diameter at neck. The diameter at neck is 15 millimeters. The diameter at neck is 15 millimeters. Okay. So that even brings us back to this concept. So if the diameter at neck is 15 centimeters, then it means that the first diameter, we have to calibrate it. We have to give it a name. Okay. So this becomes our original diameter now. Okay. And then the new one we are coming to write becomes our hot. Since it was 15 millimeters, the new one we are going to write, we are going to name it as what? D1. Don't get confused. This is now going to become our D1. 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 Good students should do well to write this, all of some of these things down. So that even if the lecturer does not send them the lecture video, still they have some evidence or something to rely on. As I told you, don't trust anyone. Yes, you don't have to trust anyone. That is one advice I wish to give each and every one of us. You came individually and you will be living individually. Focus on your goals and achieve them. If you end up putting your trust or your hopes in someone, and at the end of the day, you end up being failed by them, human beings change each and every day. It may lead you to a whole lot of consequences. And in the university, you really need peace of mind to be able to work effectively.
Yes, ma'am.
You,
Nunca se menina, ma'am.
yeah.
Isso bem.
Okay, so let's proceed. Also, since this is 15 centimeters, let's quickly write that down. 15 millimeters. 15 millimeters. This, we all know, the length is also known as the gauge length. What is the question asking us to calculate for? The first one said we should calculate for the Young's modulus. The first one said we should calculate for the Young's modulus. The second one also says that we should calculate for the stress at elastic limit. The stress at elastic limit. We're also supposed to calculate for the ultimate tensile stress. The ultimate tensile stress. And also the percentage elongation and the percentage reduction in area. As you can see, some answers have been provided over here. And these are what we are going to be using to test for our answers, whether they are right or not. Okay. Since it is a load extension curve, the formula that we are going to even use to calculate for our elasticity, as we all knew initially, was stress over what? Elasticity is equal to stress over strain. Yeah, so that is the formula we are going to adapt. Let's quickly move to our solution and make history. So this is the solution. This is the solution. This is the solution. This is the solution. This becomes the solution. Mhm. From here, what are we supposed to do next? Let's proceed to solve our question. And this is our question A. Yes, the A says we should calculate for the, let's say, the Young's modulus. So we are going to write over here Young's modulus. So this is the Young's modulus, the Young's modulus, the Young's modulus, the Young's modulus. So for this case, our Young modulus, the formula we're going to be using to calculate for our Young modulus is equal to what? Elasticity is equal to stress over strain. So our elasticity is equal to stress over strain. Stress over strain. Stress over strain. As simple as that. Stress over the strain. From here, what are we supposed to do next? I told you that this is the same as what? As we all know, the stress is equal to what? Load over area. Uh-huh. So let's quickly write that down. But in this case, it's not just any load, though, and it is not also just any area. Okay. Due to that, the first thing we're even supposed to do is that to avoid any form of uncertainty, let's go and calculate for our areas first, since we have different diameters. You understand me? Uh-huh. Since we have different diameters. So we want to calculate for our area first, quickly, before we come and now do what? Uh, solve for any other thing else, as we all said initially. Good students fail to contribute to the lesson, leading the lecturer to do all the work. Good. So we are going to calculate for the original area. So the original area AO is equal to pi d squared over 4. Pi d squared all over 4. But in this case, it's not also just any d that we are going to use. Okay. Due to that, what are we going to do? We have to investigate that since it's the original area we are calculating for, that means that we have to use the original diameter. Okay, we have to use the original diameter. And this that we have written over here is the same as what? 3.142 times this thing. But let's even do our substitution. Let's even do our substitution and make life much more easier. That means that our AO or our original area is going to be equal to what? 3.142. That is 3.142 times the diameter. Okay. You realize that all the diameters that was given, it was even given in millimeters. Okay. So life was even made much more easier. Good. So let's continue. Our diameter, the original diameter was 20 millimeters. So let's write that inside over here, 20 millimeters. Let's close the bracket nicely. As simple as that. All over 4. All over 4. So our original area AO is now going to be equal to, let's all good students should do well to point this together with the lecturer. Remember to square this. Remember to square this as you are seeing over there. Good. So let's all do that together quickly. Point the division sign on your calculator. Enter 3.142. Okay. Times open bracket. Let's say 20. Enter 20, close the bracket, square it, bring your cursor down and punch 4. You're going to get 1571 over 5. Punch SD if you can see SD on your calculator. And now you are now going to get 314.2. Okay. According to the laws of indices, you realize that these guys over here, they already have an exponent of 1. Okay. Since they are equal, this is going to affect them. Okay. So this is going to let it become what? Millimeter what? Squared. Exactly. 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 So this is our original area. This is the answer we had for our original area. Let's quickly calculate for our area. Okay, our area of the rod at failure. So that is the A1. So A1 is equal to pi times D, and it's not just any D. D1 squared. D1 is the what? Diameter at fracture. D1 is the diameter at what? Fracture. As I was saying. So you realize that all over 4, all over 4, all over 4. So this becomes what? Our A1 is now going to be equal to our pi we are adopting is 3.142. Okay, times the D. And which D are we going to use? We say we are going to use the D1 is the diameter at fracture, which is the 15 millimeter that was given in the question. 15 millimeter you are seeing over here. Good. So let's put the 15 inside here. That is 15. Let's add the millimeters. Exactly. We square all of this. We divide all of this over 4, as you are seeing over here. Finally, what are we going to get as our answer? You realize that our A1 is now also going to be equal to, you can edit the initial one you did on your calculator if it's still available, and we are now going to get 176.7375 millimeter squared. That is 176.7375 millimeter squared. We are going to get 176.7375 millimeter squared. Now we can just proceed to solve our work quickly, as easy as that. Good. So we are done calculating for our original area. We are also done calculating for the area at fracture. Okay, so let's take our question A, which says we should calculate for the Young's modulus. The Young's modulus. Young's modulus. Good. Good. From here, what are we going to do next? The formula we want to adapt is what? E is equal to stress over strain. E is equal to stress over strain. Stress over the strain. Good. Stress over strain. From here, we said that this formula we are seeing over here, the elasticity is the same as what? Stress, as we all know. This over here, as we are seeing, the stress is not just any load we are going to use. The strain too is not just any hot strain we are going to use. Okay. To be able to get the Young modulus, take note that the Young modulus only occurs in the straight line. Let's go to the drawing. You see the first straight line I drew over here. Sorry, because it's a broken hand I used to do. It's just a free line sketch. You may see it like that, but this is actually the straight line, okay, in the graph. So it occurs there. So we can only pick a value from the straight line. And in this straight line, it is only 80 kilonewton that has a load of zero, that has an extension of 0.25. Okay, that we can pick. Okay, so let's pick the 80. Let's adopt that for the calculation of, let's adopt the 80 kilonewton for the calculation of our stress, and adopt the 0.25 for the calculation of our strain. Exactly. Exactly. So this, we are not going to use anyone, just as we are saying. So the load, we are going to use what? The load at what? In the straight line all over what? The A. Okay, all over what? The original area. So this one too, we are going to use what? Our strain is just going to be change in length over the original length. Change in length over the original length. Okay. So that, as we are writing over there, could also be written as what? P over AO all of this into brackets divided by change in length over the original length. Finally, what are we going to get? Finally, what are we going to get? Let's quickly substitute our figures into the question and see the answer we can get from this. So the load, we said that we want to adopt the 80. We want to adopt the 80. Can you see the 80 over here? This is the 80 we are going to be using. Let's quickly punch it inside. So 80 kilonewton, that is 80 times 10 exponent 3. 80 times 10 exponent 3. 80 times 10 exponent 3. All over the original area. So the original area is what? 314.2. 314.2. 314.2. Good. Exactly. We divide this. The change in length. What is the change in length we are going to adopt over here? What is the change in length we are going to adopt over here? Our original length in our question was given to us as what? 20 millimeters. You see. So no, our original length was given as is the gauge length, and that is the 200 mm. So that is the 200 mm. So we write that over under here beneath the denominator, 200 mm. So that is it, 200 mm. And also, if I want to put in the unit, this one is going to be in Newton. This is in millimeter squared. And this is in millimeters, as you are seeing over here. The extension we are going to use is the one that is corresponding with the 80 kilonewton. Look at it in the graph. That is the 0.25. The 0.25. Check it out over here. It was already in millimeters, so there was no need to do any conversion. Okay. It has an extension of 0.25 under a load of 80 kilonewton. Good. So we are just going to put that over there. 0.25. Okay. 0.25 millimeters. Millimeters will take care of millimeters, and life is going to be much more easier. Let's confirm the answer. Let's all confirm the answer. Who has gotten the answer? Anyone who have gotten the answer so far? All right. So let's all quickly punch it. Let's all quickly punch it. You can punch your answers in the comment section. You can punch your answers in the comment section. You can punch your answers in the comment section. So at the end of the day, so you realize that at the end of the day, I'm getting 203. Okay. So that is it. At the end of the day, I'm getting E to be equal to 203,691.916 Newton per millimeter squared. Exactly. 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 Let's move on to solve our different question. So you can see our first answer is very precise. Let's calculate for the other one. Stress at elastic limit. The stress at elastic limit. So you're just going to use the load at the elastic limit to calculate for that. That is it over here. So the B is the stress at elastic limit. Please, any question so far up to where we have gotten to? Any questions so far? Any question so far before we proceed? All right. All right. So I can see that Patricia AC has gotten the answer, and that was very, very, very awesome. Let's proceed to solve the other ones. Let's say this is our stress at elastic limit. Okay. Let's calculate for the stress at elastic limit. So this is the stress at elastic limit. Stress at elastic limit. Stress at elastic limit. Let's calculate for our stress at elastic limit. From here, what are we going to do next? Because it's our stress at elastic limit. Stress at elastic limit. So, stress at elastic limit. So, at the end of the day, we are just going to use the load at elastic limit all over. So, let me write it over as this. Stress at elastic limit is equal to what? The load at elastic limit all over what? Original what? Area. Because you know that stress is equal to load over area. Okay. And this is going to lead us to get an answer of what? So our stress at elastic limits now become equal to, let's go back to the question, and our load at elastic limit, or even let's go back to our page 1 and look at our drawing. Look at the drawing. This is the drawing. Okay, in the stress at elastic limit was 102. Check it out over here. You see, and the load at elastic limit was 102, as we are saying over here. So 102, this is what we are going to use to calculate for our question. Let's proceed. That is what we are going to use to proceed. So that become the 102 times 10 exponent 3 times 10 exponent 3 all over Newton. Okay, all over what? The area we calculated for. And the area, we are going to use the original area, that is 314.2. 314.2. 314.2. 314.2. 314.2. So let's all point this together. That is 102 times 10 exponent 3 all over 314.2. At the end of the day, what are you going to get? Quickly punch your answer in the comment section and let's see. I had 324.633. Okay. Depending on the depending depending on the let me say for the pi, okay, depending on the values that was used to solve for the work. If the pi of the person was more, you know that pi is a bit plenty. So if the pi of the values were more, then at the end of the day, the person's elasticity may be a bit different from ours. Okay, that if you are using the real pi on the calculator. Okay, but just because we are using maintaining 3.142, that is why there is a bit form of variation in our answer. Okay, for teaching purposes, I have to adopt this part. But if you use the real pi on the calculator, you realize that life is going to be much more easier, and your answer is going to be very similar to that in the slide. But this is also very, very much precise, and this is 314.2 millimeters squared. Okay, so after we did this, I'm getting this to be my stress at elastic limit. That is 3. Let me see, some people have the answer in the comment section. That is Sappho got it right. Dave got it right. Exactly. Nee also got it right. Nee also got it right. And also Patricia AC also got it right. Exactly. So that is 324.633. 3, 3. Let me just maintain it to here. So let me say 4. Okay, 4. I just run it. So that become um Newton per millimeter squared. Newton per millimeter squared. Newton per millimeter squared. So let's solve our question C quickly. Let's solve the C part quickly. Let's solve the C part quickly. So this is our question C. And what is C saying we should calculate for? C say we should calculate for the ultimate tensile stress. That is just the maximum stress. Okay. Ultimate tensile stress. That is the tensile stress. So the ultimate tensile stress, the ultimate tensile stress, ultimate tensile stress, ultimate tensile stress, ultimate tensile stress. And the formula that we are going to adopt in this case is going to be what? So this kind of stress is the same as the what? The maximum stress. So that is the maximum load. Okay. So the maximum load over the original area. The original area. We've already calculated for the original area, so we are good to go. We are good to go. So you see, So let's just substitute our values into the formula, and let's see the answer we can make from this. So our maximum stress is now equal to what? From our diagram, our maximum stress is 130 kilonewton. 130 kilonewton. So let's quickly point that over here. That is 130 kilonewton. 130 kilonewton. So instead of the kilo, let's just write times 10 exponent 3. Okay. So that become 130 times 10 exponent 3. Okay. All over the area. 314.2. 314.2. Okay. Millimeter squared. This is Newton. So let's all point this together on the calculator, and let's see the answer we are going to get. So our maximum stress is going to be what? What is going to be the answer for our maximum stress? That is what? 130 times 10 exponent 3 all over 314.2. 314.2. So let me check the comment section. Okay. Okay. So I can see a lot of people are precise. Okay. So I think we are all on the same size. We are all supposed to be getting. Let's compare that to our slide. And that is what? Maybe it was not stated over here, but we are supposed to get 413. 413.749 749 749. Okay. So let's just add our units. Let's say Newton per millimeter squared. Newton per millimeter squared. Newton per millimeter squared. So as simple as ABC. As simple as AB. That is our maximum. Let me say that is our maximum or ultimate tensile stress we have calculated for. That is our ultimate tensile stress we have calculated for, or maximum tensile stress. So let's calculate for our percentage elongation. That is our D percentage elongation. percentage elongation. D. D is percentage elongation. Percentage elongation. Percentage elongation. Percentage elongation. Percentage elongation. Percentage elongation. As simple as that. And what did we say is the formula for a percentage elongation? So that the percentage elongation is equal to the total extension over gauge length expressed as a percentage. Okay, that is our percentage elongation. Our percentage elongation. That is, let me say, our percentage elongation. Our percentage elongation. Our percentage elongation. That is our percentage elongation. That is, let's say, our percentage elongation is equal to the total extension, okay, over the gauge length times 100. So this is the original length, which is also known as the gauge length. The numerator, you put total extension over here. Not just any kind of extension or any kind of change in length, the total, all of them, the addition of all, total extension. So this is going to give us, what is our total extension? From the graph, let's move to page 7. And our total extension was what? 56. You see, 56. So let's put that down, 56. That is 56 over here. 56 millimeters over the gauge length, which is 200. We all know times 100. Let's all do this together and see the answer we are going to get. Let's all point this together. This is also in millimeters. This is also in millimeters. This is also in millimeters. Okay, that is 56 over 200 times 100. So you're going to get 28%. You're going to get 28%. Darko was right. You're going to get 28%, 28%. So this is going to give us 28%, 28%. So the percentage reduction, you can calculate for that one too quickly, and then we wrap up for the day. That is the percentage decrease in area. Percentage decrease in area. So the percentage decrease in area, the percentage decrease in area, percentage decrease in area. Now is going to be equal to what? Or let me say the percentage reduction in area. Percentage reduction in area is equal to our percentage reduction in area is equal to our original area minus the area at fracture. That is the A1, okay, all over the original area times 100. Quickly point this into the calculator and tell me the answer. Let's all do this. Let's all do this together quickly. Quick. So this is going to give you, I remember this one, we had 314.2, 314.2. Let's do for this one too. We know that it's 314.2. 314.2. Okay, minus, let's go to page 8 to see that. The A1 was what? The A1 we had 176.7375. 176.7375. Good. Let's go back to our initial position. Let's use that over here. 176.7375. So let's close that quickly. Let's multiply all by 100. Quickly tell me the answer. We have few seconds to go. So finally, what are we going to get? Quickly punch this together. 314.2 minus 176.7375. Close the bracket over 314.2 times 100. We are going to get 43.75%. 43.75%. 43.75%. 43.75%. Thank you very much for your time. May God richly bless you all. If you are facing any challenges, please do well to see me in groups one-on-one. Also,